Okay, so the whole point of today is really to derive the equations of motion of the double pendulum. And it seems like typically the way that's done is using this thing called Lagrangian mechanics. Now, from my cursory reading, you can derive the equations of motion by defining a value L to be the difference between the kinetic and the potential energy expressions of the system. Then using the Lagrangian, apparently you can derive the equations of motion. So we're going to try to do that. Um, and but I actually want to understand it. So I'm not like, okay, so let's just write down what the to-do list thing is here. First off, I think I got to go push code from my other computer. And then what's the change here? I think there's no actual change here. I think it's all just a bunch of malarkey. Yeah, so just for that. Okay, I will be back in a moment with my code pushed and another cup of coffee. Okay. Maybe we will do a Cartesian. Wait, what? Oh. Or actually, how do I do a dotted line? Arrow. Surely there's a way to make a line that's dotted. There we go. Now, what about an arc? There's no way to make an arc? That is insane. You can't do this without a you can't do this with the trackpad. It just doesn't work. Choose Cartesian coordinates for each mass. If cos is 0, then it's at minus L. That makes sense because the origin is at the pivot point. So that's okay. And then x2 is equal to, okay. Okay, so the positions here are really easy. That's fine. Now the kinetic energy, the velocity is followed by time differentiation. I see. So here's a chain rule, because you take, so this was sine, and then it became cos theta d theta, or d theta dt, theta dot. And then you just do that. But what does this represent? So this is the amount that it's changing in x. So that checks out. This makes sense. This makes sense too. So the kinetic energy is actually a really simple equation. Because kinetic energy is a quantity of work. Work is the energy transferred to or from an object by the application of force along a displacement. But then why is it saying that work? Wait, where was that? Okay, hold on. I'll be right back. I hate that they use distance for S in this equation. Displacement should be D. But anyways, that's okay. Why would S equal AT squared over 2? Oh, because S is, bro. Yeah, because S is a position. Yeah, oh, that's so simple. Okay, that's fine. All right, so let's go back to the. Okay, so now that I remember what kinetic energy is. Oh, no, because it's 1/2 mv squared. Right, that actually makes sense. Because this is v squared, so um, the velocity is the square root of x squared plus y squared. All right, so this is the kinetic energy of the system. Oh, and this is totally in terms of thetas, so that's perfect. So that's all good. Okay, let's figure out what the potential energy of the system is. So, okay. If I take a pendulum, a single pendulum, and I move it to the top, the distance it travels is going to be 2L. So that means that the amount of energy it has, potential energy. So potential energy is also a work, right? I'm pretty sure potential energy is also a work. So yeah, so then if you figure out what the work done is between so you're so okay, so let's figure out we need to rederive um help me derive the work required to take a single pendulum, 1 kilogram, 1 meter length, from rest to the very top. Because what did they say the angular version of work is? It's the torque times theta, the angle. And I'm pretty sure that the inertia. Oh wait, we need to sync changes. Oh, we should probably start this whole thing up because this takes forever. So, but wait, let me find the equation because the torque. Yeah, because the potential energy, because this is going to be mass times acceleration times distance. But is it more work to move it along the 2 mgl because L is the radius. Okay. Does it not take more work to move it up around the pivot versus if you could move it straight up? Because if you just lift something up, maybe it's like the same. It probably has the same potential energy, so I think it doesn't matter. Oh, that's cool. Ah, yes. The path matters if there's like friction or something else. Okay. So, um, so let's get back to deriving the potential energy then. So the potential energy is just going to be the sum of potential energies. Okay, form the Lagrangian. So this equation minus this equation for each generalized coordinate. Okay, so this is the Lagrange equation. It's that the change in the Lagrangian with respect to the first ddt of the change in the Lagrangian with respect to a dependent variable minus so presumably okay, so this I need more background on this. Okay, so then you get two equations. And you know, I'm curious to see if Julia can actually do what we want. So, all right, so let's try to rewrite it now in terms of this. So I think this is probably going to be like, all right. I thought modeling toolkit 10 was that. What's holding it back? Something's holding it back. Probably, I don't know what's holding it back. Anyways, This will probably take a long time. So let's just start. Okay, so let's just copy the using modeling toolkit, and then I guess this. Let's get these two guys. Let's just copy everything. I feel like Grosvenor really let us down, so we should probably remove that. Grosvenor was such a letdown. Thing doesn't even work. Okay. I mean, how does it take that long to solve a single quadratic formula? All right. We need to. How do you declare it? It's at model. They have like they have so many macros. So okay, this is gonna be double pendulum. This looks pretty good. We're just gonna get rid of this. Okay. So, we start with, we're gonna comment these out because presumably it can reduce it to first order. This should be minus 9.8, right? I need to stop updating. I need to just stop updating. That's what I'm gonna do. This is the last time I'm updating this thing because it just takes way too long. Okay, so let's see if we actually learned anything. I'm gonna turn off Copilot. Copilot is not helping. Okay, so the first thing that we can do, I'm pretty sure, can you introduce new? So this only serves as intermediates. They're not real systems. So okay, so remember that. Am I able to put comments in here? It would be cool if I could annotate equations, but I doubt that works. Okay, so the Lagrangian is equal to t minus, what do they call it? U? I forget what they call v. Why do they make v the? Okay, I'm not doing that. Lagrangian is equal to the k minus the p. I wonder if I can just embed things in here. The kinetic energy of a single pendulum is 1/2 mv squared, where v is equal to L times theta dot. Or, oh, wait, you need to do backslash uppercase dot. How did they get the theta dot? Is that a real thing? Okay. I guess not. Because how how fast it's moving is the length of the pendulum times how fast it's moving in angles. We can also use Cartesian coordinates. So, hold on. I'm gonna get my camera and I'm gonna get I'm gonna get on the whiteboard and try to draw some of this stuff out because right now I need to stand up or something. They're not showing up. Oh wait, you know what? Okay. Why am I being so dumb right now? What is going on? Okay, so that sort of makes sense. No, yeah, that makes sense. Okay, I don't know why I was tripping. Yeah. Okay, that checks out. That's not hard to understand. So x1 is going to be equal to L1 times sine of theta 1. Let's just keep it like that. X2 or y1 is equal to minus L1 times cos theta 1. Now, now we can just do x2 is equal to x1 plus this, and y2 is equal to y1 plus, oh, we need to fix this, I forgot. This is 2, this is 2. Okay, so I think we can actually just move this and change these equals to. Let's see if this works. Can you do this? Please no compilation errors. Please no compilation errors. Cache miss. Cache miss. Okay. So we understand that. Okay, well, I guess what I'm trying to understand is. Okay, we need to understand the V2 expression. So, when that is only the speed of the second mass relative to the moving pivot at the end of the first rod. Okay, that's okay. I mean, it really doesn't matter. All right, so we got this. So now what we want to do is K1 is equal to, and this is going to be yeah, 1/2 times m1 times, this is going to be v squared. So let's just say v1 is equal to, this is going to be, well, v1 squared is equal to, this is going to be, oh yeah, wait, we didn't write down this yet. We only wrote down the, but we should be able to just write d of x1 squared plus d of y1 squared. Because if we take, let's just, we have symbolics, right? So at variables x1, y1, theta 1. Or wait, actually, can we just do at parameters L1? So if we did x1 is equal to L1 times sine theta 1. Okay, then we have this expression. If we do d of x1, expand derivatives. Oh, wait. You know what we have to do, though? The reason why that didn't work is that theta 1 is of t, like that. We don't really need the x1. The x1 doesn't actually matter. So if we do this, and that's of t, and then we expand derivatives. And did it do the chain rule? Yes, it did do the chain rule. Okay, good. So at least it knows that, right? That's the important part. Okay, so then we're going to get m1 times v1 squared. Okay, then this v2, I think, do we do this? I think we do this. I think we make them all tildes. So v2, we can just change all this to 2, and same with this. This is going to be the kinetic energy of the second pendulum. Right, so we get t, which we're calling k. Uh, Whoa, it stores them as strings and then it parses them later? That's interesting. Okay. Now, what is the potential energy of the system? Okay, then let's just add a comment. The potential energy is just how much we have lifted each mass from rest. I.e., so we're going to have P1 is given by um, um, wait, this looks more accurate. I think that this looks way more right than. Oh wait, actually, no. Y is wait. Okay, in this, what is Y? Because it's L1. I think that it seems like it represents its deviation actually. Because wait, if um oh no, never mind. Let's say theta is pi over 4. Single pin. Then y1 is equal to minus L1 cos pi over 4. So y1 is greater than y rest, meaning cos or theta equals 0. Okay, then the potential energy is m times g times y1. But that doesn't seem to make sense, right? Because then it's going to be m times g times minus L1 times cos pi over 4. Wouldn't this mean at theta 0? Okay, if this is 0, cos 0 is 1. So then the potential would be very negative. But shouldn't it be 0? I think because the potential needs to be 0 when it's straight down. Oh. We're given the absolute vertical. Yeah. Oh, you can have negative potential energy relative to. Oh, wow. Okay. Damn, I'm starving, bro. Hungry. Okay, but I feel like I'm finally getting somewhere. That is so cool. Okay. I don't think you can just give the Lagrangian to Julia and it'll work. I think you have to. I think you have to. Okay. So P1 is just going to be given by M1 times um, G times Y1, right? L is given by K minus P. These timelines are hilarious, bro. But we could do that. The question is whether or not this all computes out symbolically. I think it does. All right, so we should look into this. Oh, nice. That actually looks pretty good. Okay, so in my notes, I'll just put this down. Notes. Lagrangian support. And then just collect the links. There's this. This. And this. All right, let's see how. Okay, so there's a function that takes in what looks like That's nice. T does not occur in here, which is fine. Oh, that's an interesting system. Oh, cool. Oh, oh, that's so cool. Dude, Lagrangian mechanics was actually really clever. Okay, so okay, I'll be right back. Okay, so the fundamentally most important thing is that I'm just using the Euler-Lagrange equations, but I'm not actually understanding why it works. So we need to go back to this and understand a more broad thing. So Lagrangian mechanics is a formulation of classical mechanics founded on the principle of virtual work. Lagrangian mechanics describes a mechanical system as a pair M and L consisting of a configuration space L and a smooth function, or M, and a smooth function L within that space called the Lagrangian. For many systems, L is equal to the the kinetic energy minus the potential energy. The stationary action principle requires that the action functional, oh my god, what? The stationary action principle requires that the action functional of the system derived from L must remain at a stationary point. This constraint allows the calculation of the equations of motion using this of the system using Lagrange's equations. So I didn't really get much from that. I don't know if anyone else is going to get anything from that. Newton's laws and the concept of forces are the usual starting point for teaching about mechanical system. This method works well for many problems, but for others the approach is nightmarishly complicated. For example, in calculation of the motion of a torus rolling on a horizontal surface with a pearl sliding inside, the time-varying constraint forces like the angular velocity of the torus, the motion of the pearl in relation to the torus, made it difficult to determine the motion of the torus with Newton's equations. Lagrangian mechanics adopts energy rather than force as its basic ingredient, leading to more abstract equations capable of tackling more complex problems. Particularly, Lagrange's approach was to set up independent generalized coordinates for the position and speed of every object, which allows the writing down of a general form of Lagrangian, total kinetic energy minus total potential energy of the system. And summing this over all possible paths of motion of the particles yielded a formula for the action, which he minimized to give a generalized set of equations. This summed quantity is minimized along the path that the particle actually takes. This choice eliminates the need for the constraint force to enter into the resultant generalized system of equations. There are fewer equations since one is not directly calculating the influence of the constraint on the particle at a given moment. For a wide variety of physical systems, if the size and shape of a massive object are negligible, it is a useful simplification to treat it as a point particle. So for us, the configuration space is um, is um, is is just going to be theta 1 and theta 2, I believe. These are all specific points in space to locate the particles. A general point in space. Okay. All right. So then they take the time derivative of each one and they get the velocities of. In Newtonian mechanics, the equations of motion are given by Newton's laws. Net force equals the mass times acceleration. Oh, man, I'm so tight right now. Dude, like, I mean, like, holy cow. Okay. No, this is fine. Okay. Yeah, so I think what we need to do is we need to derive the we need to apply Euler-Lagrange to the single pendulum. All right, but let's just read this whole thing just in case we get anything out of it. The potential energy of the system V reflects the energy of interaction between the particles, i.e., how much energy any one particle has due to all the others. Together with any external influences. It is a function of the position vectors of the particles. It is a function of the position vectors of the particles only. For those non-conservative forces, which can be direct. Bro, this is too much for me. This is just not a good article, man. That's the problem. It's like it's too. There's a clever repackaging of Newton's law so that you never write down the internal constraint forces. See, okay. I hate that they use T and V, bro. Why not use K and P? Speak English. It's just so confusing that V, which you think of as velocity, is used as potential. But whatever. Then the condition that the action integral be stationary. Okay, first let's do the Newtonian pendulum because I don't recall ever solving for the tension to get eeks of motion. Then, all right, so let's just do that. Let me think about my plan here. This is what I want to do. I want to do a single pendulum eeks with Newton. Then I want to derive. Then I want to derive the Euler-Lagrange eeks for, or then I want to. Let's just do a single pend with with Lagrangian. Okay, then what am I doing? Then I want to derive the Euler-Lagrange. Derive Euler-Lagrange. Because I don't really get it. I mean, like, how do they teach? Bead on a hoop. Okay. Let's start by doing the classic Newtonian derivation with a single pendulum. Okay, so you write. Okay, so they write it in this vector form, that's fine. Then the tension along the rod. So this is pivot L. I don't know what that is. Define coordinates at the bob. Oh, okay. You define coordinates. And this is from your. Yeah, this is L sine theta, this is minus L cos theta. Okay. So this okay, so this is okay. Wait, why actually the yeah, that the tangential velocity or the tangential acceleration makes sense, but the radial doesn't. Radial acceleration comes from the fact that even though the bob's speed might not be changing in the radial direction, its velocity vector is constantly changing direction as it swings. Now project x and y's acceleration onto the unit vector. A good video. I'm gonna watch it again. There's this one. This is the one that I liked.
Hello and welcome everybody, my name is Elliot, and in this physics mini lesson, I'm going to give you a quick introduction to the three formulations of classical mechanics, aka Newtonian, Lagrangian, and Hamiltonian mechanics. Newtonian mechanics is what everybody learns about in their first physics class when they learn to apply F equals ma to simple systems. But there are two other formulations of mechanics that are actually more widely used by modern physicists, and they're essential for understanding quantum mechanics, meaning the physics of very small objects like elementary particles. These are the Lagrangian and Hamiltonian formalisms of mechanics, and in this video I'm going to teach you the basics of both. I'm going to illustrate each approach using the simple pendulum as an example. So we've got a particle of mass m hanging from a lightweight rod of length L, which is attached to a pivot at its other end. Now, I'll assume that you've already learned how to
Okay, hold on.
analyze a pendulum using F equals ma, so I'm only going to review that briefly right now before I get into the Lagrangian and Hamiltonian approaches. But I've posted a whole other video just reviewing the basics of pendulums that I'll link below, so you can check that out if you want to see more of the details. And I'll also paste a link to some notes that I wrote about these topics, which you might also want to check out after you've watched this video. First of all, we need to set up some coordinates to describe the position of the pendulum. We can use whatever coordinates we want, but it's simplest to use either the arc length coordinate s that runs along the circumference of the circle traced out by the particle. We can use whatever coordinates we want, but it's simplest to use either the arc length coordinate s that runs along the circumference of the circle traced out by the particle, or we can use the angle that the rod makes with the vertical, theta. They're totally equivalent, and either one will do the job for specifying the position of the mass. The relation between them is just the definition of the angle theta in radians. It's the arc length s divided by the radius L. We want to predict how the pendulum is going to move when you pull it up to some initial angle and let it go, or if you were to give it a little kick. According to Newton, we should start by writing down all the forces that are acting on the particle. There's only two of these, gravity mg pointing straight down.
Okay, wait, let's just think. If S, what is arc length? Arc length is like pi. Well, it's got to be, the arc length has got to be theta times L. So if theta is, let's say pi, and the length is 1, then the arc length is also pi.
And the tension T in the rod pulling radially back toward the center of the circle. Then Newton tells us to add up all the forces and write F equals ma. The total force equals the mass times the acceleration. F equals ma is a vector equation, but what we're really interested in here is the tangential component, meaning the component of the force and the acceleration that point along the circle where the particle is constrained to move. The tension isn't contributing anything here. That's pointing straight toward the center of the circle.
So that's why I feel like the Newtonian pendulum isn't even the best example to motivate the Lagrangian, because it's like, this goes to 0 anyways.
Which is perpendicular to the tangent direction. So the only relevant force is actually the tangential component of gravity.
So that's why when we derived the equations of motion for the single pendulum, we didn't have to do any of this. We didn't have to do any of this tension stuff.
Geometry work, you can see this is mg sine theta pointing back toward the pendulum's equilibrium position. So F equals ma for the arc length coordinate s simply reads ms double dot equals minus mg sine theta. I'm using dots here to denote rates of change with respect to time. So if s of t is the position as a function of time, then s dot equals ds by dt is the velocity, and s double dot is the acceleration, the second derivative of s with respect to time. I want to write everything in terms of theta though, so I'm going to use the fact that s double dot is equal to L times theta double dot in order to rewrite the F equals ma equation as theta double dot equals minus g over L sine theta. This is called the equation of motion for theta. It's the differential equation that governs the motion of the pendulum. And it's actually pretty complicated in this case because of this factor of sine theta on the right-hand side. Too complicated, in fact, for us to be able to write down a simple solution in general. There is one special case when we can, though, and that's when theta is small. meaning that the pendulum never gets very far away. If you
Boo.
want to know how that works, check out the other video that I posted.
Boo.
This looks like. I'll paste a link below so you can go play with it too. You drag these little sliders here to set the initial angle and initial angular speed of the pendulum, and then press start to let it go and see the resulting motion. When I release it from a small angle like this, you can see that theta versus t indeed looks like a cosine function. So I hope you'll go play with this. Try choosing different values for the initial conditions by dragging those sliders. Draw for yourself what you...
Bro, let's try it.
you think the graph of theta versus t should look like with those initial conditions, and then press start to see if you got it right. Alright, so that's a quick review of how we understand the motion of the pendulum using Newtonian mechanics in F equals ma. But there's a lot more to mechanics than F equals ma, and in the years after Newton's work in the late 1600s...
Okay, so let's just rewrite that down so I have it on the board. Why not? Man, I wish the lighting was a little better. Okay, that's fine and all, but the part that I don't understand is the part where he does the conversion from, like, why is ms double prime?
Position. So F equals ma for the arc
Because
length coordinate s simply reads ms double dot equals minus mg sine theta. I'm using dots here to denote rates of change with respect to time.
I guess it makes sense because the force is on the tangent, so it's I get that the tangential force is minus mg sine theta. But why is it m times s? Because in the tangential direction, your coordinate is the arc length. Yeah. Okay, that makes sense. All right, let's get to Lagrange.
More challenging. But they're both really fascinating and they provide new insights and strategies for solving problems. Remember that it's also totally fine if you don't follow every single detail that I present here. What I'm really hoping is that you'll be inspired to go off and keep learning more on your own. Alright, let's look at the Lagrangian formalism next. Whereas Newton told us to start by writing down the total force, Lagrange tells us to start by writing down the kinetic energy, the potential energy, and then taking their difference. This defines a function called the Lagrangian, L. Let's see what the Lagrangian is for our pendulum example. The kinetic energy K is of course just 1/2 mv squared, where v equals s dot is the speed of the particle. Actually, I'd like to write everything in terms of theta, so I'm going to replace s dot with L times theta dot. Then the kinetic energy is 1/2 m L squared theta dot squared. The potential energy U, meanwhile, is just mg times y, the height of the particle above some chosen ground level. I'm going to put ground level at the height of the pivot. Then the y-coordinate of the particle is minus L cosine theta, and the potential energy is minus mgl cosine theta.
Hold on.
So,
I want to make some food. I'm getting hungry. Dude, this whole project is making me love classical mechanics. Classical mechanics is actually sick. I don't know why I had a hex. The thing that's stupid is that the course that I took on classical mechanics, it was just like it was just like they never emphasize why it's so cool. They just are like, here's what it is, but they're never like, look at all of this cool stuff you can do with it. It's actually so tragic because this stuff is really cool. Even this is not that motivating.
So
I
the
mean,
Lagrangian for our pendulum is the difference between the kinetic energy
sort of a
and
separate
potential
thing,
energy. That's 1/2 ml squared theta dot squared plus mgl cosine theta. So Newton told us to start by writing the total force and setting it equal to ma. Lagrange instead tells us to start by writing the Lagrangian like we have here, and then using it to write what's called the Euler-Lagrange equation. That's d by dt of dl by d theta dot equals dl by d theta. By the way, the curly d's here stand for partial derivatives. If you've never seen those before, don't worry about it. For practical purposes, they behave just like ordinary derivatives. Now, I'm not going to get into too much motivation as to where this Euler-Lagrange equation comes from in this video.
at least he said
What I
that,
just want to
you
do
know?
for now is write it down and investigate the consequences. But the short answer is that the Euler-Lagrange equation is the condition for the action S to be minimized, where the action is defined as the integral of the Lagrangian. Euler-Lagrange equation is the condition for the action S to be minimized, where the action is defined as the integral of the Lagrangian. The claim is that of all the possible paths that a particle could follow, the one it actually chooses is the path that minimizes, or more precisely extremizes, the action. This is known as the principle of least action.
Well,
And
I mean, see, that's actually the cool part. That's actually so fucking cool, man. Wow.
the implication is that the trajectory satisfies the Euler-Lagrange equation. But unpacking all of those details would really require its own dedicated video. Right now, I just want to see what happens when we plug the pendulum Lagrangian into this Euler-Lagrange equation. The right-hand side of the Euler-Lagrange equation is the derivative of L with respect to theta, and we're going to treat theta and theta dot as independent variables when we take these derivatives. That means that the only contribution to dl by d theta comes from the cosine theta term in the Lagrangian, and we get dl by d theta equals minus mgl sine of theta. For the left-hand side, we need to know what dl by d theta dot is, and from the kinetic energy term, we get ml squared theta.
Okay, wait, hold on. So this is a Lagrangian, right? And the change, let me think about that. So, all right, let's just talk about like linear velocity and acceleration. So theta dot is going to be our velocity. So let's say we have something moving at some rate, okay? If we're trying to take the derivative of its velocity with respect to its position, yeah, that doesn't make any sense. That goes to 0. So then you just get my, okay, cool.
Theta dot. Then taking d by dt of that just turns theta dot into theta double dot. By the way, dl by d theta dot here is called the momentum p corresponding to the coordinate theta. dl by d theta is called the generalized force. The reason for the terminology is that the Euler-Lagrange equation is then reminiscent of Newton's second law. Force is the rate of change of momentum. So the result of plugging in our pendulum Lagrangian into the Euler-Lagrange equation says that ml squared theta double dot equals minus mgl sine theta. Canceling out the common factors, we once again obtain theta double dot equals minus g over L sine theta. The same equation of motion we obtained earlier using F equals ma, but this time we got it using a very different strategy based on the Lagrangian and the Euler-Lagrange equation. All that might seem a little bit abstract if you've never encountered a Lagrangian before. But in fact, it's a very useful way of quickly getting at the equations of motion for a system, oftentimes easier than using F equals ma. If I'm faced with most any mechanics problem,
Okay, so let's do this. Let's switch over. Let's do it. All right. Can we get the white balance fixed? It's so dark. It's so dark. We need to. Maybe I'll just try to mess with it on here. That's no good. Let me see. It's a little better. I turn up the contrast. It's a little bit better. I think that looks a little bit better. How did he do the potential?
replace S dot with L times theta dot. then the kinetic energy is 1/2 mL squared theta dot squared. The potential energy U, meanwhile, is just mg times y, the height of the particle above some chosen ground level. I'm going to put ground level at the height of the pivot. Then the y-coordinate of the particle is minus L cosine theta, and the potential energy
Is that right?
is minus L cosine theta.
Or no? 'Cause is that right?
That's one.
Wait, no, I flipped it around. gonna be honest, I don't really understand the Euler-Lagrange equations. It seems like the EL equations say that the change in L with respect to velocity, so this is in parentheses, with respect to time, is equal to change in L with respect to position. But see, that seems so weird. The change in the... Okay, so you have this Lagrangian. It's the difference between the kinetic and potential energy. Then if you change the velocity... If you see how the change in velocity, or the change... That's so bonkers. I definitely do at some point want to derive the Euler-Lagrange equation, because I don't see why that's... I don't really get it. But that's okay. Well, let's see. Conjugate momentum. Partial L, partial Q dot is called the generalized momentum associated with Q. Okay. Okay, actually, you know what? Now that they say that, that kind of makes some sense, right? Sort of. I don't know. All right, so let's derive it. Let's get the equation of motion for the pendulum. You know, I'm gonna turn off that filter. I don't like the filter. Yeah. All right. So then, Okay, well, that's that. Okay, so that's cool. So now I actually feel like maybe I can derive the Euler-Lagrange equations for the double pendulum. Because it's not that hard. It's really not that hard. It's just boring. Okay. Cool. Okay, so I think we're gonna do that. And then so now we're gonna do so I'm kind of skipping, so I want to do that after. Oops. Wait, why does it think that this is a Julia file? That's funny. All right, so what we're gonna do is we're not gonna do double pendulum with Newton. We're gonna do double pend Lagrange. Then look at the code in MTK links below, because I want to understand what exactly Ingbo wrote. V goes to Q dot. Oh, he gets it. Oh, this is so sick. He traces it through. Then he gets the F. F would be for what we had. That is the dl d theta. And then I don't know what Q is. Then L sub V is the gradient with respect to V. But then you need to take that dt, right? So I guess he does that in the equations. So then right hand side is equal to sub F minus the Jacobian. I don't get that. The Jacobian of this with respect to X. I don't know why you would do this. I don't get this line. Times your velocity minus the derivative. Okay, so this one's good. So this one makes sense to me because that is the ddt of d theta or dl d theta dot, because v is right, and then he just substitutes for the original symbols, and then m. Well, he uses a backslash here. M is some matrix describing the Jacobian of we need to try this out, see what this code does. And then okay, what are the equations of motion? We're getting too advanced because this is too general. We need to start with a simple example and then we'll do the complicated example. Though this is so cool. So cool, man. And I mean, this guy already did an end pendulum. We'll see if we can get that working too. All right. I'll be back. Oh shoot. I wrote a bunch of stuff on the board. It's a little low. Let me just um what I got stuck on is figuring out how do we get the velocity. Is that right? I guess that's true. It's going to be the change. I feel like I want to just sit down and compute some examples with that. Because, like, what is this equation really saying? It's saying that. Okay, wait. Let's hop back over. Well, Okay, so that now we just need to figure out the potential energy, right? So the potential energy is actually pretty easy to figure out. Okay, so we've derived the Lagrangian, except I just didn't write it all the way out. But I think I'm just gonna write it out on my computer because it's just so long. Okay, so let's just start out with x1 is equal to L1 sine theta 1. X y1 is equal to minus L1 sine cos theta 2 or theta 1. X2 is equal to x1 plus L2 sine theta 2. Y2 is equal to y1 plus L2, minus L2 cos theta 2. Okay. So these are our Cartesian coordinates. So V1 is going to be equal to or let's just say u is equal to the list x1, y1 maybe. u2 is equal to, so u will be our vectors, x2, y2. Okay, so then I think u dot u, is that equal to x1 squared plus y1 squared? Okay, good. So, but I don't like this notation as much. It's shorter, but it's not as clear to me. So then this is going to be v1, or so then we do this. And I think it should just leave it wrapped in a square root head, right? Yeah, so then we can just say that this is v1. And v2 is equal to, all right, so now we have our velocities and our coordinates in terms of theta 1 and theta 2, which is cool. So now we want our Lagrangian. So first off, we're going to say K1, or let's just do K1, is equal to the kinetic energy of the first particle, which is going to be 1/2 times m1 times v1 squared. K2 is equal to 1/2 times m2 times v2 squared. Okay, then K is just equal to K1 plus K2. All right, now we have the kinetic energy of the system. This is the kinetic energy of the system, K. So now we want to figure out what the potential energy is. And the potential energy of the first particle is going to be equal to m1 times g times y1. And P2 is equal to m2 times g times y2. So then P is equal to P1 plus P2. Sum of all the potential energies. So you get the total potential energy of the system. So now we have the total kinetic and the total potential. And so now we take our Lagrangian L is equal to K minus P. Kinetic minus potential. And then we get this big old expression. And so now what we want to do is we want to do the Euler-Lagrange equations. So let's just let d theta 1 equal to d of, oh, and you know what? We actually need to reevaluate everything because I think that these need to be of t. Yeah, these are of t. So we need to actually evaluate all cells. Okay, there we go. So now we want to say d theta 1 is equal to d of theta 1 of t respect to t. Okay, great. And then we just want to do the same thing. Oh, shit. D theta 2 is equal to d of theta 2 of t respect to t. Okay, so now what we want to do is we want to do d of L with respect to d theta 1. Oh, wait. You know what? I messed up here because it's not the position. This is not right. We need to let dx1 equal to d. So wait, this needs to be of t. Can I do that? Am I allowed to do that? Huh. But if I did like x1 of t, does that work? Are you allowed to do that? For some reason, I'm a little bit not confident that this is right. Okay, then this is going to be dx1, dy1. This is going to be dx2, dy2. Okay, wait. Now let's rerun all cells. Because I think maybe I'm just supposed to do, because, okay, if I go back to this, if I have x1, if I just do dx1 of t, what does that give me? See, I think maybe that's what I'm supposed to do. I don't think I'm supposed to add the, I don't think I'm supposed to, I think I'm supposed to delete these things. So if I just delete those, and then we reevaluate. Okay, so let's see if we can get the Euler-Lagrange equations and then see if it's right. So this is, okay, that's fine. So what we want is, and then d t. So that is the first one, and then we have this one. So this is going to be equal to, so wait, let's get the right hand side. So then we're going to get, so this is like left hand side 1, right? Because it's d dt of partial Lagrange partial theta I. So this is, or partial theta I dot. And that's going to be equal to d of, so this is going to be right hand side 1 is equal to d of L d of theta 1. But you know what, I'm a little confused. So d theta 1 is of t, right? So what we need is that right? Okay, so then this is this is left-hand side 2. D, okay, and right-hand side 2 is equal to D of L, theta 2 of T. And then we get our eq is equal to this list where we have left-hand side 1 is equal to right-hand side 1. And left-hand side 2 is equal to right-hand side 2. Can I do copy? For the Lagrange double pendulum. These guys really insist on the T and V. But I don't buy that stuff. Oh yeah, can we do a yeah, let's do that. So the expression, so let's do a let's do this minus right hand side. Okay. All right, so we got the Euler-Lagrange equations. Now let's just get them into Julia, right? All right, so let's try to do that exact same thing. All right, so I'm not going to do it. I'm just going to do it double. So at variables, we're going to get theta 1 of t, theta 2 of t. Okay. Then we're going to say that x1 is equal to, at parameters L1, L2, M1, M2. Now we want to get our Cartesian coordinates, which is just going to be L1 times sine of theta 1. Y1 is equal to L minus L1 times cos theta 1. X2 is equal to x1 plus L2 times sine theta 2. Y2 is equal to y1 minus L2 times cos theta 2. They've absolutely got to ban loud motorcycle. These people, these people are the worst people on the planet. Like, I actually think the motorcycle people that just love to disturb everyone are the worst people on the planet. Insane. I mean, how I just don't understand how anyone could be that disrespectful. All right. So we got our coordinates. Now what we want is d of x1 of t, right? Oh, we can't do that. D is what? Differential of t. So d of x2. All right, so d of x1 squared plus d of y1 squared, square root v1 is equal to this. v2 is equal to square root d of x2 squared, or let's just do this. All right. All right. Now we just need, now that we have the velocities, we need to come up with the kinetic. So wait, v1 squared, is this just, okay, wait, see, but if I do simplify, it's so funny. It's like, how did it not simplify this? Let's just do v1 squared equal this v1 squared 2 squared. Let's do v2 squared. Okay. All right, so let's do k1 is equal to 1/2 m1 times v1 squared. K2 is equal to the same thing. Let's just oh, that's not going to work. Okay, 2, 2, 2. Okay, so now we get k is equal to k1 plus k2. Oh my gosh. Implicit conversion to float. Absurd. In symbolics, you care about precision. All right, so now we want our potential energy. So P1 is going to just be equal to M times M1 times G times, oh yeah, we need to do G, times Y1. P2 is equal to M2 times G times Y2. Okay, so now we have Euler-Lagrange, okay? Or no, wait. So now we have the Lagrange is equal to K, P is equal to P1 plus P2. Okay, so we have the Lagrangian. Now what we need is d let's do d is equal to differential of t, right? Oh, we can't do that. Okay, fine. D theta 1 is equal to differential of theta 1. And then we can just duplicate this and turn this into a 2, and then we get d theta 2. And so now what we want is we want we want the derivative. I think we just do we not just do d theta 1 of L? I think that's correct. But then we need to do d of this, right? And this is given by oh wait. Wait, I didn't do this right because we do need those. We do need these. But then we also need d theta 1 is equal to d of d theta 1 and d theta 2 is equal to d of d theta 2. I think that's everything. So then we get d of d theta 1. So that's correct. Oh, wait, no. This is correct. So then, and then is given by d. This is going to be, so this is going to be the derivative of the Lagrangian with respect to the position. So this is going to be d theta 1 of L. Wait, why is that not right? Oh, this needs to be a differential. Wait, that doesn't seem right either, though. Okay, so wait, we need to disentangle some stuff here. So what we're trying to get no. So what we're trying to do here is we're trying to get this just needs to be d theta 1. This needs to be d. There we go. I think that is right. Because what this represents is the differential with respect to the angular velocities. Let's comment this out. Okay. So, now the real question is that going to actually work? Because it looks like they did some special stuff to, like, I don't think that you can just, like, even in this example, actually, maybe it will work. I wonder, can we do a ND solve? Okay, wait. I'm curious to see if this still works, because certainly this worked at one time. Ugh, you gotta be joking. That is one of the worst things about it. There's no way to clear. It's like man, MATLAB had that 50 years ago to be able to clear something away. That's okay. We'll replace it. That's okay. Damn. Where did that fail? In the creation of this dictionary? All right, we'll need a. I'll be back. Wait, do we have? Nah. What is Q? Q is the third argument. Okay, so we have up to here. Now we just need to figure out why this dictionary. This needs to fail, right? Okay. So why does that fail? You know, actually, let's just do this. Oh yeah. I need a walk. I'm gonna go on a walk for like 5-10 minutes. Okay. Wow, how did this get 104 views? So we need to, before we do anything, I want to simulate it with this. So why did that fail? Okay, what if we tried this again? Let's delete this. Sick. Okay. Nice. So what is this? Theta 1 double D rule. I don't even know what that means. What is this? It doesn't have a. I don't think I need to manually first orderize it. I'm pretty sure that it'll do that for me. So then if we just take sol 1. So these are our eeks. These are the eeks. Let's say EL or my eeks. So then I want to, and then let's just get, we'll write our parameters out. So the system, what do they say? I'm not going to first orderize it. That's not, okay, so let's just, ND solve probably won't work without, so let's look at the documentation. ND solve. Oh, but you know what we want to do? Actually, we want to do my eeks slash dot peaks. We'll call these peaks. So this is going to be a list of rules where we get G goes to 9.8, M1 goes to 1, M2 goes to 2 or 1, L1 goes to 1, L2 goes to 1. Are there any other parameters in here that I'm missing? What about initial conditions though? Oh, we need it. We provide those in the eeks though. So, okay, so wait, if we do this, are we missing anything? I think that those are the only parameters. Okay, so in that case, then we need IC eeks, which is going to be that theta 1 of 0 okay, so this is theta 1 of 0. Wait, how do we, come on, we need more examples with initial conditions. Because where did it, y of 0, oh, so you do equals. So equals. So theta 1, say pi over 4. Theta 2 of 0 equals pi over 4. So they're both bent. Okay. Just make sure that this does what I want. Okay, so then we want all eeks is equal to flatten peaks, parameterized eeks, and IC eeks. I don't understand. It's because there's no nesting. It's just two. What? Maybe it's just join. What if I have like this? Join. Okay. Okay. So now we want to do nd solve of all eeks. What is that? That's going to be the dependent variables. So we're going to get theta 1, theta 2, and then we want t 0, 10 seconds. Equation or list of equations expected. See, but they do this tensioned. They don't do this with a Lagrangian. What if we just do Wolfram Lagrangian solve diff-eq or something? Which is actually not what I want though. So why didn't this work? I don't get it. These equation or list of equations expected instead of, oh, you know what? Oh, that's so annoying. Because we need to change. So these are rules, unfortunately. So these eeks. I wonder, actually, you know what? If we have my eeks, I think this is the power of symbolic programming. If I just do slash rule goes to equal. Ha! That's dope. See, now that's dope. That's why I love this stuff, because you can just change the expression. It's not that hard. All right, so we get the eeks. All right, let's try it again. So we got the eeks. Wait, why didn't that work? Because peaks are like this. And then we got this. And then we got this. Number of constraints is not equal to the total differential order of the system plus the number of discrete variables, 4. So the whole point of that is that what we want to do, I think, is we just want to make, I think, all right, wait, first let's just evaluate. If I do theta 1 of 0 prime, what does that do? But what if I do, is that the same as theta 1 prime of 0? No, I think that those are two different things. So then I think what we want to do is theta 1 prime of 0 is equal to 0. Theta 2 prime of 0 is equal to 0. So let's just delete this. Okay. So we got the ice eeks. Now we got these eeks. And now we got this. And I think we need to do let's see, is there more examples that's not a freaking scalar differential equation? I mean, what a joke. Okay, so see that. So, okay. So I think that this actually might be okay. Oh, let's freaking go. Let's go. Okay. I'm actually just going to save this notebook. All right. So we simulated the double pendulum using the Euler-Lagrange equations. Pretty happy with that. Evaluate all cells. All right, so now we just got to get it into Julia. And the thing is, honestly, we could just take the equations, right? Well, these equations, my eeks, and just use them, right? Like, we don't actually necessarily need to have the computer algebra system that we're using do the derivation, even though that's obviously better because then you don't have to look at the equations like that. But if worst comes to worst, we can just do it the dumb way. Okay, so now I have, so the thing is though, if I do, let's see, if I do theta 1 prime, does this work? Nice. So these are the equations in which it solves in. So I got this to work, but I want to make an animation that shows the double pendulum. Is that possible? Whoa. See, that's kind of the annoying part. So let's just okay, so let's just that's the problem, man. It's like I don't like that it does that. Bro, why would it do that? We don't have a lot of time. Yes, that's what I said, and it didn't listen to me. I literally said that. Why would you just name it something else? Are you dumb? I mean, it's like so dumb. Why would you clear my stuff? There you go. Fucking dumb shit. You damn idiot, bruh. Why did it fail? Hold on. Let's do this. P rules equals this. Dude, stop. I hate when it does that. I just don't know why whoever designed that, man, it's just like so annoying. Just whatever. We're so close. I can feel it, man. Let's go. This is gonna do it. I promise. Please, please work. Ugh, I don't know why it makes it multiple. Why does it make it oh, because the freaking semicolons, dude. Right? Is that why? I don't know. But it really, really bothers me. Is it running or what is going on here? Oh, sick. That was really cool. Why is it going so slow? Wait. There's probably a frame rate. So wait, I like that default duration is 10 because then it's real time, or I guess, but it seems way too low FPS because it's I mean, is that right? Oh, is that what you do? That looks pretty good, man. Can I download this? Oh, wow. How do I download the video? The crazy thing is that's an expression. That to me is the craziest part, is that that's just an expression. What's up, brah? What is going on, man? We're trying to simulate the double pendulum. Let's you know, this is the thing about these notebooks though, is it makes it really annoying to, so let's set this to be like 3 pi over 4 and this to be like pi over 4. And then let's do this. And we're gonna resolve it. That doesn't look right. That doesn't look right. But that's okay. No, that looks right, dude. That looks like the double freaking pendulum, man. Nice. That rules. Let's go. Yeah, man. Yeah, it's for my final project. I'm doing it with a group, but my group isn't really there. I mean, a couple of them are trying, but like, I don't think they're used to coding. I don't think they, because I mean, I'm with like a bunch of 20-year-olds, so it's like I don't really expect a lot. But all right, now that we have this, I basically just need to rewrite it in Julia so that I can simulate it, but I need to understand this code that I found online. But I'm gonna make some food right now because I haven't eaten all day and I'm starving. So hungry. I don't know what there is to eat though. Well, yeah, the professor's definitely like, you guys are the farthest ahead, but I haven't really said, oh, I used to simulate differential equations professionally, so it's, you know. Oh, nice. Sushi sounds good, dude. I love sushi. I'm gonna see what I have. All right, I'll be right back. All right, I'm back. Sorry about that. Okay. Oh man. Hope you're still here. Me. All right. What are we doing? Okay. So I don't understand why this. Why does this not work? It's like a weird error. V Q dot. Oh, you know what happened? That's weird. Because yeah. Okay, I see why. I see why that happened. So the problem is Q dot is V omega. Let's just call this VV. Um, wait. What is the original code? Instead, let's just call this vels. So we have, but V, no, wait, so we need to rerun this thing. Okay. All right. We're getting there. Okay, so this is the first error. So now we need to take that code and figure out. First off, I think wait, hold on. This needs to be vels. I figured. Let's just do collect dot. Damn it. Fuck. Wait, why doesn't this work? Whatever. I don't actually care. Okay. So let's just fix this to be this. Really? What? This doesn't work? The thing about writing it in terms of the Euler-Lagrange equations, it's much more flexible. Like, for instance, this Q. Dude, this is so cool. That's why it's so nice to be good at linear algebra. If we call lag on okay. If we call lag on vels x, and then what is p? This is p. Okay, so we get the Lagrangian, which is a scalar thing. But now if we take, so let's just say this is LF, right? Then we call modeling toolkit dot gradient of LF with respect to X. So this is going to be that right-hand side, right? Because X represents the positions. Now that looks a little sus to me. But I honestly don't know if it is. Okay. Bro, I'm going to take all of these and I'm just calling them LV. I can't stand. All right, so now if we take gradient of L F with respect to vels. Okay. Now what the hell is this right-hand side? So you take the Jacobian. Okay, so this is going to be LV. So the Lagrangian with respect to the velocities. Now if you take Jacobian, does this work? It's not exported. Great. Modeling toolkit of the vels with respect to the x's. Is that what you want? I feel like you only want the diagonal of that. Oh wait, but these are not. What am I talking about? These aren't even the double pendulum equations. Okay, wait. So sweet methods for these. There are probably 1,000 methods. That's great. What are the best ones? Do they rank the best ones? Okay, so we need to make sure that this is. Does that work? Cannot convert in as something of type. Bro, what? I don't understand. Okay, wait, so what we need to do is we need to just remove this. Remove this. All right, so surely, or what is Q? Q is, shit. So we have this, then we have this. And we want to change this to like this. Okay. Now we got this. Got this, and that didn't work because of some dumb stuff, I'm sure. Sim L, what is L? So L is actually supposed to be, oh wait, you know what? This is lag. Okay. Then we got this gradient here. Got this. Okay, if we just Google the Euler-Lagrange equations, how do they usually present it? I like that the equation is not even. So maybe that's what they're saying that. Okay, so we should really go through this. I don't get how. Oh, because the Jacobian times Q dot, this is probably a vector or a matrix vector multiplication. Oh, because Q dot's a vector. Ah. Okay, so what is this? So first up, is M even a matrix? Okay, it is. M is the LVV. LVV. Um. Okay, wait. So what was this then? I think that the thing that we need to do is scalarize. Okay, there we go. Now it's a vector of equation. All right. So I think we finally debugged the function. Not that I understand it, but if Ingbo wrote it, it's definitely correct. You know? What did I do now? Okay, wait. So let's go back to the way things used to be. I think if I just restart from there. I think collect works too, right? Whatever. Let's just do collect. All right, let's just try to run all this code. Wait, did this not work? All right, we can try this later. Oh yeah, we need to do this. Oh, we don't really need any of this. We need Q dot. We don't need this, right? Because we have what did they originally pass as Q? Q is the forces. So this is Q. So we actually want to take this, comment it out. You know what I can do? I can get fancy with it. Wait, can I? I think I can get fancy with it. God. What? Oh my god. Now that is a bug that would be hard to debug. I don't know how we're going to debug that. mtk compile slosh. What? Where's my golf example? Oh, this is just a sys, right? Or is this some intermediate type? Oh, we don't know. Okay, I don't know. Let's try this. What is it? MTK build. See, I think though that this is not gonna work. I think you're supposed to just do. Yeah. See, it's expecting a binder to a function, but I don't know. Ugh, God, that's fucking brutal. So there's something wrong with these equations then. See there? Do you see this? Okay, so we need to actually collect these two. So what if we try that? No, see, okay. This backslash, I think on both of these, you need to go modeling toolkit.scalarize. And then maybe we'll broadcast it across all of them and hope that works. God, so stupid. They should have, dude. They should have never freaking. How do you get rid of this? You need to simplify. Okay, wait. All right, here's where the solution lies. If we just return m right hand side, okay, and then we just do. Okay, we got m, which is this matrix, and then we got right hand side, and we do. So first off, collect right hand side. Okay, we get a vector. Now we do m backslash. Ah, damn it! It just doesn't work. It's just broken. That is such a joke. So the backslash doesn't work or what? Did it used to work? It's because it's not a num. If we do 1 unit of, does it take a type? How do you do this again? I don't even remember how to do this. Let's see. Let's just say x. Is x a scalar, right? Or oh, okay. I see the path. So the problem is that right hand side. Or wait. Let's see. The problem here. Can we call num on? Okay. So what we need to do is we need to call collect, and then we need to call num dot. Okay. I think I got it. Okay, wait, let's return this again. And we do this. And then we just do m backslash right hand side. Let's go. I'm a fucking goated. I'm goated. All right, that's great. So presumably now the equations are actually well formed for this god awful type system. Please. Let's fucking go, dude. Let's fucking go. Okay. Oh, what a relief. So now all we have to do is call this function. We define the Lagrangian, which is easy. So, relatively easy. No, the Lagrangian is easy. I already did the Lagrangian. This is the Lagrangian. But the thing is, I don't know if this Lagrangian is... I think it's okay. Okay. The thing about this... Oh, no. So this is a function of time. And it probably could be a function of theta... But I would be fine if it was only of time.
Let's just double check that we can solve this thing. Okay, so we got the cis. Motherfucker. Very good. Okay, so I think what is going to happen is that's all pretty much for today. The next thing to do is going to be basically actually understand this code, figure out what the generalized forces are for our muscle activation. Okay, figure out all right, that's it. That's it. End of stream. Okay, that worked out pretty not so bad.